Welcome back to our study of supervised learning. This is video 3, linear methods for regression, and the second unit of this course on supervised learning. We're going to continue talking about supervised learning and the ways that we can use it. However, this time we're looking at numerical outputs. Remember, regression is when we are looking at a supervised learning algorithm that is looking for a quantitative output, a numerical output. So let's dive right in and see what that entails. And again, this is a presentation by EDU Onyx. Okay, so linear regression models and least squares. Let's really quickly talk about regression versus classification. In classification, we are looking for a Boolean output. Yes or no. Is this object in a particular class? Yes or no. When the output is a numeric value, what we want to learn is not a class, but it is a numeric function. In machine learning, the function is not known, but we have a training set of examples to draw from it. So the goal, learn a numeric function. And then we can use that numeric function to get the numerical outputs that we are searching for via linear regression. All right, so the linear regression model. This is going to look exactly the same to the linear model that we generated in the previous video where we talked about linear methods for classification. Here again, as introduced in the second video, we have an input vector x of t, and this is the transpose of x since x is a column vector, and we want to predict a real valued output y. Once again, the linear regression model has the following form. The linear model either assumes that the regression function is linear or that the linear model is a reasonable approximation. So we're also going to have inputs, and these inputs can come from a variety of sources. Previously, we've looked at just the example of quantitative inputs where it's directly coming from our training data. However, we can also have transformations of quantitative inputs such as the log, square root, or square, polynomial representations such as basis expansions, and we can also have interactions between variables. So we're not going to dive into this in too much detail yet, because in video 5 we're going to talk about these things, specifically basis expansions and regularization. But just know that our inputs don't necessarily have to be the training data specifically. They can be variations of that data. So no matter the source of the inputs, the model is linear in the parameters. That is the assumption that we are making going into this linear regression tasks. We are assuming it's either linear or linear models are a good approximation of these parameters. So in prediction tasks, we can have interpolation, where we would like to find the function f of x that passes through our training points. In polynomial interpolation, given n points, we find the n-1 degree polynomial that we can use to predict the output for any x. We can also have extrapolation, where if x is outside of the range of x of t in the training set, in a time series prediction, for example, we have data up to the present and we want to predict the value for the future. For example, if we're looking at stock trends, we'd want to know what the stock was doing in the future, not based off the past training data, and this would be called extrapolation. Finally, we have regression, and this is when there is noise added to the output of the unknown function. The explanation for the noise is that there are extra hidden variables that we cannot observe. So we have a subset of the actual data. Our training data does not encompass every data point. However, we only have a small subset of that. So we're going to add some noise, and we're going to spend a good portion of this video talking about that noise and how it's added in these regression tasks. So solving with least squares. Again, least squares is one of the best methods that we have to estimate our parameters beta from our training data. In this method, we first pick the coefficients beta to minimize the residual sum of squares, which we talked about in the previous video, learning linear methods for classification. From a statistical point of view, this criterion is reasonable if the training observations represent independent random draws from their population. Even if the input data, the x's, were not drawn randomly, the criterion is still valid if the observations y's are conditionally independent given the inputs x. So this is a good criterion for regression tests. On the bottom, you see beta written as the unique solution, again, in matrix notation. This is the same as classification tasks. However, we're not going to have an outlying rule that switches our output y into, for example, we talked about orange or blue classes. We're just going to use those parameters beta to generate our numerical function. So let's talk about the data distribution assumptions really quick. Up to now, we have made minimal assumptions about the true distribution of data. However, in order to pin down the sampling properties of beta, we now assume that the observations of y are uncorrelated and have constant variance, and that the x's are fixed or non-random. So we're going to have in our data an input x, and then as a result, we're going to get an observation y that is uncorrelated to the other observations y. So those data are going to have a variance denoted by sigma squared. So we can predict or estimate the variance using this function. And this is just saying that in our output data, there is going to be some normal Gaussian variations simply based off of statistical properties. And we're going to account for that through the use of this variable sigma. So let's take a look at what this means when we actually apply it to our least squares. So linear regression with error, again, we have the same least squares minimization, and we're looking for a linear model now, though, that has an error value. So we now assume that the linear regression model is the correct model for the mean, that is, the conditional expectation of y is linear in x. However, we also assume that the deviations of y around its expectation are additive and Gaussian. Hence, we get the following equation where the error epsilon is a Gaussian random variable with expectation 0 and variance sigma squared. And that can be written as follows, where the epsilon is approximately equal to n of 0 and sigma square. That is, epsilon has an expectation 0 and a variance sigma squared. So now our linear model has been updated to account for this slight variance in our output distribution. So we have an error value epsilon built in here. And remember, beta naught was that parameter that was specified as the bias. Important terminology to know from these is both bias and variance. When we're going forward and we're trying to tune the parameters of our model to best fit the data, you're going to be adjusting the bias and variance. And that's why we're really diving into these formulas, because it's important to know where the bias and variance are coming from and what they actually signify in the data. So moving on, we are going to go back to our example where we looked at predicting the price of a used car. So in this graph, we have price and mileage, and we have several data points denoted by the x's, and they have been fit using a linear model, a first order linear model, a second order linear model, and a sixth order linear model. So these are all polynomial fittings of different degrees. When the order of the polynomial is increased, the error on the training data decreases. But as shown by our sixth order polynomial here, a higher order polynomial follows individual examples closely instead of capturing the general trend. So you see the sixth order polynomial is dropping off significantly towards the end of our graph here on the right side according to x in mileage. And that's probably not representative of the general trend of this data. So this implies that Occam's razor also applies in the case of regression, and that we should be careful when fine-tuning the model complexity to match it with the complexity of the function underlying the data. So Occam's razor, we're assuming that the minimal amount of assumptions necessary is going to be the best way to model the data. So the learner is evaluated on its predictive power of a test set instead of the training data. And again, this goes back to generalization. We want a model that doesn't fit the data exactly, but captures the overall trend of the data so that it can generalize to future predictions very well. So when you're doing a linear regression task, make sure that the polynomial or the linear model that you're outputting is not overly complex, but instead matches the complexity of the underlying data. So that is linear regression. And a quick summary, when the output is a numerical value, what we'd like to learn is not a class, but a numeric function. And this numeric function is often a polynomial of varying degrees. The important terminology from this video are bias and variance. We talked about bias first in the linear methods for classification, and that's essentially the intercept beta naught with the y-axis in our input space. And variance is going to be absorbed by our error, the addition to our linear regression model, and accounts for the Gaussian distribution in our output data y, because it is independent in y and dependent on the x value, and the variance here accounts for those different distributions of data. So when you're tuning your model parameters in later videos, bias and variance are all parts of these linear models that we are developing here. So our next video is going to be talking about the support vector machine and kernels and flexible discriminants within that. And I'm happy to dive into that. That'll be an exciting video. Thank you for listening.